Thank you, everyone. Am I audible there? Yeah. So, the topic that I have is reversing deep learning models, right? The journey of AI has started from a typical regression problem to the now we have a multimodal architectures over there, right? But the foundations remain same. Eventually, if you look at the hype that is happening from the AI security point of view, right? So everyone speaks only about LLMs. But there is something much more beyond that. When you are doing some prompt injection, right? You are just attacking from a perimeter or the peripheral part over there. But if you understand what is deep inside the model, you will get to know some of the big secrets about that model. And it becomes easy for you to create the better attacks and also secure model better. So now to start with, I'm Yashodhan. I'm doing my PhD currently in satellite security. I have a couple of masters and done a couple of research in different domains, including space research, IoT security, IoT product development, AI product development. And when I working on the security part, I thought AI security is something very much needed at the moment, and let's focus on that. Then, to begin with, when you design any AI model or develop any data science problem, right, you can see the model is at the core. So, any development or design over there starts with a business requirement. What problem are you solving with those data science or AI statement, right? Based on that, you have a requirement. You have to have a gather requirement. Then you have a data. So data can be from the multiple sources. It can be from IoT sensors. It can be from some websites, right? A number of sources. And it can be the multiple sources as well with a different thing, right? And once you have those things, you need to have a specific set to create that particular model. And for that, you need to have these different operations in terms of cleaning the data, right? Having that in the right format, right? And eventually, you need to have some right feature selection from that data that fits to that particular model. Because the model is going to learn from those features. And eventually, once you have the model, you're deploying that model on some on-premise or a cloud server, right? So, and then all MLOps comes. So with the MLOps, it's not only DevOps, it comes with the retraining approach of that particular model as well, right? So we can see the model is something very critical and at the center from this perspective. The model is going to tell how critical an attack can be and how it is going to resilience against that attack. Now, just to discuss about, security from an AI point of view, right? So here, when we have an IT system or IoT system, CI is dominant, where confidentiality is a dominant. If you go to the OT systems, the ICS domain, availability is most important over there, right? So AIC is something. But now, when you come to AI, it is ICA. The integrity gets a tick. And the challenge is, we are trying to integrate AI in multiple domains. So eventually, you cannot treat AI as simple applications. You need to treat AI as a system. It has its own challenges. It has its own set of rules. And those set of rules come from the mathematics. And those mathematical and statistical rules need to be followed if you are securing the AI part. So, this is a very foundations from an AI perspective. Rather, if you, separate out the foundation components of AI, it is basically the data, these algorithms, and the model. These are the three foundation things of any AI systems over there. And these are the foundations asset. So if I want to do any kind of threat modeling for AI, I just cannot do only stride in terms of what is identity, what is authentication part of that. That is still at the surface level. But from a model perspective, you have to understand what is that AI is going to do that. What is the purpose of that model? And accordingly, you have to have the threat modeling for that. And you need to address this ICA from a dominance perspective for those particular model. Well, now, when we come to any AI models, so since we are speaking about reversing those models, we should know what are the formats, right? If you have done the firmware reversing over there, right? There are a number of formats that you get, a bin, bind format, and many things are there, right? Same thing happens with these AI models or DL models, right? So as you can see, the different models, so you can see on the part that's onnx stands for Open Neural Network Exchange. This is a open source interoperability kind of a format. Basically it has, I think it follows some Google's protobuf structure over there. And the good thing about that is it can be deployed on the different premises of a cloud. You can deploy on the edge devices, and also you can deploy that on the microcontroller, considering the fact that I should have a RISC architecture, at least the SIMSys RISC architecture from the ARM, and the kind of, it should have a FPU, floating point unit, and then it can support something called as a SIMSys neural network library, where these models fit can basically convert into C code, which are nothing but some of the weights of the neural network, which can then you integrate your C code and integrate with actual C code, and you can deploy that on your microcontroller level. So it can start inferring over there. So this is one of the famous protocol mostly used in a couple of DL algorithms. Then coming to the next, something called as a safe tensors. Eventually, the Hugging Face organization, which is hosting different AI models on their website, right? They are kind of came up with the transformer architecture, which is again the foundation for the LLMs. What you have a GPT. Basically, it's a transformer, right? GPT stands for, it's basically transformer. T stands for the transformer over there, right? It's a transformer architecture. That's the library that they have over there. And they have come up with the format called as a safe tensors format, right? So what the tensor means? Tensor is nothing but a mathematical structure, which is having some dimensions. So if you have studied this mathematics in class 12th, you must be knowing the algebra, like matrices, right? So you have a matrix which has the 2 dimensions. Likewise, if I keep on increasing dimensions, I can classify them as tensors. Rather, I can classify vectors, matrices, everything as a tensor. Right? So that becomes easy for anyone to design that AI model over there. The good thing about safe tensors is they address some of the vulnerabilities associated with serialization attack over there. So that way, there are some security they come up, but of course, there are some challenges also. But most of the large language models are using safe tensors, including deepfakes. If you go to the Hugging Face and see all the deepfakes libraries, or not libraries, the models over there, I think they have 52 models over there. They are all safe tensors. Then it comes the symbol of a PyTorch. The PyTorch was designed by Meta, which is again a tensor-based framework, and they have a particular format like .pth or .pb. And later, from a Google uncle, we have TensorFlow Lite. TensorFlow again works on tensors, and TensorFlow Lite is kind of a library or kind of a format that can still deploy on edge devices as well. So these are the important formats exist from the perspective of the large language models or the deep learning models, whatever existing into the current one. Right. So what we'll just go a couple of architectures. We'll understand what are the architectures and what is the reversing of those architectures mean over there. Right. So this googlenet is an architecture which is also called as an inception. Of course, it's quite a, I think, 8 to 9 years old back architecture, and it was considered to be the computer vision architecture in terms of identifying the object. This particular architecture is considered the base architecture for other its successors like VGG, AlexNet, ResNet kind of stuff. Right? The why I've chosen this because from my laptop perspective, to do some attack, it's easy to on these particular file over there. Otherwise, it becomes very complex and it takes a lot of time to create those attacks. So what this particular architecture has, right? So basically, it has kind of a 22 layers. When I say 22 layers, what does that mean? When you say something I'm going to learn from the neural network perspective, so eventually we have some input And eventually you have a different combinations of, input associated with the output part. So likewise, intermediate stage, what we call as a neuron layers, right? Hidden layers, what they call, right? They have a different neurons. Okay. To clear, if you heard about these neural networks are working like a biological neurons, it's a myth, right? The biological neurons work completely different. The term that is used as an artificial neural network, the creator of that is Geoffrey Hinton, who was head of AI at Google, right? Father of AI, basically, he's now also Nobel laureate, right? So eventually he designed that as a mathematical function, but they're not like a biological neurons. Biological neurons works completely different, right? So there are different internet presentations. We'll see the synapses and different things from biological compared to that. That is all wrong, right? So eventually, if you look at this particular architecture, there are different layers, and these different layers, we have different combinations where we try to do some mathematical operations. So these operations are kind of a linear and a non-linear operations. What does that mean? When I say linear operations, it is like I have multiplication, additions, kind of a weighted sum. And then I have some non-linear operations. Because these neural networks are learning something. They want to learn the patterns. So to learn the patterns, you have to give some mathematical function so that they can understand the patterns. And then there are some activation function comes, which does the job of recognizing those patterns. And there the seed of intelligence start building into the neural network. Right? So you can see this is basically, you can see the different layers like C1, P1, right? C1 basically stands for convolution. And the core architecture that this googlenet follows is the convolutional neural network, which was the creator of that is Dr. Jan LeCun, who is chief of AI at Meta, and who was the student of Geoffrey Hinton. Right? So here what happens is we have the different convolution and the pooling combination in which the neural network is trying to learn some of the important features from the images that you get over there, right? And based on that, it tries to classify the objects in different category. So something is chair, something is human, something is car, whatever, right? So that particular object detection and recognition part is done by this googlenet. Now, when we have to do reverse engineering on this model, because this googlenet is available as .onnx format, Open Neural Network Exchange format. It also available as a TF-Lite format, right? So both way it's kind of a deployable. But when I started researching on that, right? So I thought of like let's go in a direction where I can get the detail inside it, right? And of course, initially I did not find any tools. So couple of libraries available for that, which are of course for conversion of format. And I use that from a hacking perspective, where I try to, identify some of the detailed parameters inside those, architecture from this particular file. As you can see, what are the data types over here? Like you can see a couple of matrices getting computed, right? So there are a number of layers and those things, right? But it's very difficult to understand what is inside that over there. You have to struggle a lot on each and every information over there. So I kept on searching something, and one fine day I found something as Netron, right? Of course, this was not designed for a hacking perspective. This was designed from the debugging perspective. And whatever available from a debugging perspective, it is for hacking. So it is basically kind of a flash ROM of IoT devices. So eventually what I did is like, when I load the model, inside it, I got wonderful things, right? So let's see what did I get. So this tool, Netron, is open source. You can also run it locally. So let me go over there. Right. So he is the owner of this tool, right? He has made it open source. Now what we'll do is we'll open the model, right? So googlenet 3 and the boom. So here I can now go and check entire model architecture. Entire architecture is now available with me, right? So we'll see some of the important parameters from this architecture that can be used by an attacker to attack the model and understanding some of the critical parameters of that, right? So here what happens is, you can see, as from data 0, you can see something like 1 multiplied by 3 multiplied 224 got 224, right? So this is nothing but the input to that particular neural network. What does it mean? It means that 1 is the sample, the one sample. 3 is the dimension basically in terms of images. These are the 3 channels, RGB channels that you have in colored images. And 224 cross 224 is the length and width of your pixel size of an image, right? So that is the input a particular model is taking, this googlenet model takes from the images over there, right? And then it does something like convolution. So as I shown in the previous, like it does a lot of operations, mathematical operations, right? So you can see some convolution, some ReLU, max pooling, right? So these are more mathematical. I won't go dab deeper. Otherwise it will become a typical AI lecture. I don't want to do that, right? But the purpose over here is like some of the parameters that we identify. So let me go to the presentation and then we'll discuss more about it. So first of all, these Netron helps me to break the confidentiality, understand the architecture. And then what I want to interest here is like understanding what is inside that system, what is inside that AI, right? So here, I am not going to find any passwords. I am not going to find any keys. Why? Because they are not in part of it. What I'm going to find, I'm going to find out what are the mathematical stuff over there. Because these models are made up of all mathematical functions, all statistical functions. As you can see on this part, like tensor properties is something called as a weight. Okay? So let me go to the tool. And if I just go over here, this is again kind of a convolution. And again, for this convolution operation happens, the library used called as a conv2d, which itself has a CVE reported. So someone can actually do the fuzzing with that once I do the reverse engineering part over there. Now if I go to this W, weights, this is something important to me. Any neural network that is designed, right, has this fundamental thing called as a weights. These weights determine how intelligently they are trying to predict something. This weight determines the strength of that particular neural network. It should not be always high, right? It should be optimal because it's a linear combination of the different mathematical functions from the different neurons that are combining together because I have to learn something from it. So here, if I go into the values, you can see I have a complete list of the weights I have. And as you can see, a lot of those square brackets, right? So these are nothing but the tensors. The 4 brackets means that I have a 4-dimensional tensor. Eventually I have 4 dimensions. It means that I have some important features, so critical features that are fitted into these 4 dimensions over there. And inside that whatever is there, these are the weights. Now, when any of the model is designed, the weights are most critical hyperparameter of that. This is foundations of it, right? And someone tampering into this model can get ready-made weights with him. So one can actually copy these weights, fit into it, and job done. My model is ready with that. And the funny thing is, if I go here, I can download as a NumPy file. So all the neural network I have, I can download as a NumPy, patch into the neural network, fit into it, right? So I can simply copy that. Rather, most of the engineering work for developing the AI actually goes in developing the neural network. And if that is getting, compromised, everything is in vain, right? So, so this is one aspect of that. Now, another aspect of that is when you start looking into it in detail, you will see the different functions that are being used over here, right? So, how the architecture is there. In that sense, when you go deeper into all these layers, you will understand different mathematical functions being there, right? And one can simply copy those mathematical functions and create their own models with the same thing. So, there is not much effort for that. Other than that, the important stuff happens over here. again, which I forgot. So these are the weights I spoke about. And if you come to this matrix, right? In this metric, I can understand what are the mean max values. That also helps me to create some of the attacks. But at the bottom, I have something called as a sparsity, right? This sparsity is a very interesting stuff from an attacker's perspective. Right? What happens is, what does the sparsity means? Now, as I spoke like kind of a tensors or the matrices where I'm fitting those weights, right? It is in dot format. Now, wherever I have the zero values, right? That determines what is the sparsity level of that. If in that entire tensor, I do not have any zero values, it's completely non-zero values, it is called as a dense matrix. Meaning, it is so connected, it is deeply connected neural network that a minor change in some of the weights can propagate through entire architecture. Meaning, there is a direct relation between weights and the sparsity, rather inverse relations between them. If I want to fudge something, I can take care of, look at the sparsity and understand it's a dense network. It's good for me to poison those weights. And eventually with those poisoning part, I can create a lot of fuzzing thing, I can perturb those weights, and I can manipulate the models over there, right? So this sparsity 0% is again a big threat to most of the models. Rather, the deep learning models, the AI models that are available in the market, including GPTs, right? They have all sparsity zeros, which is kind of a threat to that. So this is one aspect of that. Now, before going to the next, what I'll show also, there is one more AI model, which is similar to GPT-4's mini. So we have this GPT-4o, right? 4o mini and 4 kind of stuff, right? So from based on that, there is a Omni, I think mini Omni model is there, right? Which is a multimodal. And now if you look at the GPT-4 from the OpenAI, right? They are not only LLMs. They are not only large language models. They are the multimodals. What does that mean? Multimodals are the one which accepts the different inputs because they don't only understand the language, they understand speech, they understand audio, they understand images, they understand video, right? And they can produce as well, right? So for that, you need to have a different inputs. And over there, we have something called as a vision transformer, VIT, vision transformer, which is in terms of .pt, if you see that particular format, that is .pt, that is again from a PyTorch. So here if you look at, it has a deeper layer and if I keep on going, you can see the multimodal connection that it has, right? It's too deep, I won't be discussing that in detail, but some of the interesting stuff that can happen over here, which I can easily explain to you, here is basically the function. Let me search a function. Matmul, yeah. So the matmul is kind of a function, which is a matrix multiplication. Also it holds a couple of CVs for that. And this tensors and everything, they are the dimension sensitive, right? So if I multiply something matrix with a wrong dimension, it is going to create an error for me. Now eventually when I'm going to attack something, I can attack with some different dimension so that I can create a DOS out of it. Right? So these matrix multiplication function is kind of a dangerous in these things. Still there are more, but they are more advanced and I don't think that they are the right point to discuss at this moment of time. Well, right? So this is about the vision one, right? Vision including multimodal. It understands vision, it understands language, and the deep architecture connect to audio, the speech and everything over there, right? So this is a mini model. I have this particular paper written as a white paper that's on my GitHub. Today I'll make it public and you can go to my GitHub and look at that particular paper. It's more detailed over there. Well, now, right. So this is about the reversing the first step of the over. Now, when I continued my research, one fine day when I was traveling, I just imagine what is the architecture, right? The fundamental architecture of that, any neural network, is like I have an input, I have the neural networks, which keeps on learning, and whenever there is an error, from a expected value to the predicted value over there, right? There is a feedback, right? There is a feedback from that. And suddenly clicked my mind, okay, isn't it like a control systems? So it's a feedback control system. And I jumped my, memories to my second year of engineering when I learned the control systems engineering. Can I treat this AI as control systems? And the moment I thought, all of the concepts from the control systems comes into my mind. And all the algorithms that use in control system, the classical control theory that you have, can now applicable over here. So what are those things that we'll discuss? So what happens in control systems, that the most important, because it's a feedback, you have to look from a stability point of view. So the control system has to be stable as early as possible and as long as possible, right? Same with the neural network. I need to stabilize them, have right predictions at the right moment of time. I cannot train them longer period of time. So eventually, I need to identify what is my stability. Why should I do it? Because if I want to attack something, I should first understand whether that model is stable or not. If the model is not stable, it's easy for me to attack. Otherwise, if the model is stable, you have to have a different strategy for that, right? So it's, being the neural networks, the large language models, or the large deep learning models, it becomes very difficult to create the attack, and to run the attack, you have to run the attack for longer time. And with those longer time attack, eventually happens is like, once you fail, your time is wasted. So it's better to look at what the system is saying you. So this is basically, again, what I did is like something called as a root locus concept. What does that mean? The root locus concept means it shows the root of a system where it becomes unstable and what point it becomes stable, right? So here, if you look at this particular graph, staying negative is always better, because it shows a kind of a stability over here, but eventually those curves that are coming down, right, shows some of the points which are highly sensitive against the changes in the system, right? Changes in the weight kind of thing. Not only this, I just went ahead, and there is one more algorithm for that. It's called as a Bode plot in the control systems, which again speaks about the phase and the kind of a magnitude response, where it says, okay, can I have the system that is behaving at the high frequency, or system behaving at the low frequency, where it has a stability over there, right? And we use the same point from an attack point of view. Here what you can see is like the red one is basically the adversarial attack on the model, and the blue is my original model. Now, the point where the red line is crossing this blue, this is the point where I can create the attack. Okay. But how to interpret that in our real scenario? The thing is, if you look at this x-axis, this is the frequency in radiation per second. It is not a radio frequency, right? It's a frequency in radiation per second. What it means is that from these models, let's say I take an image for an example, right? It has high frequency and a low frequency component. What are those? So, for example, when there is a change in the border, this is the high frequency, right? When the sudden change in the color, it's a high frequency. There is a graduation change in the images, it's a low frequency. What it tells me that the model is vulnerable, the weights are vulnerable to the kind of a high frequency thing. So wherever I need to now focus on the high frequency areas of those images where I want to create those attacks, right? Same thing over here. This is again a Bode plot, but this is from a magnitude point of view. The phase part is something showing what are the frequency ranges over here, and here it shows what is the strength of it. So as you can see, the lower the strength, higher is the attack probability. So you can see the attack ratio is quite a higher over here, right? And eventually I can have a better attack at some of the higher gains system over there, right? So as you can see, from the lower perspective, as the gain is coming down, I can have a better attack. All right. So this is about the whole model. But now, eventually, if you just go back, so what I showed you, the complete architecture, right? It's a deep 22 layers of architecture, or still there are different layers to it, right? So what else I can do to save my time? So I can attack layer by layer. How to do that? So as I said, like I have this numpy file, which I can download for that particular weight. I need to check the stability of that weight. And from the first layer, what I showed you, it is the same output that on the one part you see some stability, and on the right part you see a lot of vibrations. So these vibrations shows that the weights that particular layer, the weights of those particular layer are susceptible to the high frequency attacks, right? And now I can go and attack layer by layer to weights by weights, right? So that way I can plan my attack. Well, so this was one of the result of the attack, that where the blue part was initial case where I have a clean model. When I created the attack, finally it reaches to the 0 towards the attack level where I can poison those weights over there. Of course, I cannot run this at this moment, everything, because it takes a lot of time and a lot of consume power, right? So we'll go to next point, right? So I'll show you a demo, a small demo where I have those weights perturbations. So weights are, as I said, like the mathematical functions. I need to change those weights so that I can manipulate those things, right? So sorry. Yeah. So before showing this output, as you can see, my initial weights. So I've just printed only 5x. Otherwise, the whole screen will be complete dumped with that, and I cannot show the difference, right? So you can see these are the weights at the initial part, and after perturbation, creating that attack from those points, I can change the weights, right? So over here you can see there is a minor difference in that values, right? A really minor. Why that important? Because I'm working with the dense matrix where a small perturbation can change the things, and I'm working with the high frequency. So both things applicable over here. So small weights, small change in the weights, I can create a better attack. And basically as the output of that, I have a first numpy file for that, right? So if I look at it, this is what the typical output. You can see these are the different inputs where the attack has happened. You can see the dark areas for the different number of channels. As I said, like there are different channel 1, 2, channel 3. So I'm creating those attacks at different frequency where I have the grayscale image, I have the complete white, some of the dark scale image, and these are the layers which the attack is happening over there. Of course, it's a long thing, so I won't go that in detail, right? So, but wanted to show how the weights can be perturbed over there, right? So now, other than that, I have two new repositories last month. One is tensor and one is torture. So, yeah, the tensor is for fuzzing the safe tensors, and torture is for fuzzing and poisoning the PyTorch models over there, right? So this is about my talk. So AI security, in short, AI security is not only doing the LLMs and doing the poisoning from the prompt injection part. It is the core of the model where you can do the attacks over there, right? So that ends my talk. Thank you so much.
Guys, if anybody is having any questions to the speaker, you can just raise one. We can just take a couple of questions.
Okay. Someone give.
Hey, hi. So the core attacking models, does that, the example you showed is probably an image, right? Where the, some of the sectors were highly modified. So does that also work for text tensors, or does it only work for image tensors?
Currently, So currently what I have is for the image one. But the other things like the onnx model, what I showed here, generally they don't go for a text one. So if you go to these repositories, that is also text. That works for text. So because you have to create a different attack from that perspective. The reason being, the only challenge at this moment is we have the dimensionality problem. All the input that you have from a different dimensions, right? To handle that, you need to have a very smarter way over there, right? So the domain changes, the dimension of the thing changes, the matrix tensor changes. You have to have a different attacks.
Okay, the attack you explained before, I can think of typical example like facial recognition system, like fooling the facial recognition system. But how would that attack look in terms of text? Like how, like modify, attacking the layers of the model. How will that be replicated here? in terms when the input is about text tensor, not an image
Yeah.
tensor?
So when you do these kind of stuff, eventually it start giving you wrong predictions over there. So instead of doing prompt injection attack from outside, right, it starts giving from the inside over there. That way it happens.
Yashodhan, thank you for the talk. You mentioned about Netron. Do you think other ML explainability models like Lime or something can also be used for
Which models?
Lime?
Sham.
Yeah.
Can
be used. Till the time you can see entire architecture, that's fine.
Thank you.
Yeah, please. I think.
Vivek, nice talk, but I have two strong reservations. Okay, it's very interesting talk. The way you have treated that, I can treat it as a feedback or a control system. They're inherently different. The training during the training phase, the readjustment of the weights processes back propagation through the network. It doesn't come. Although a control system works like a loop, it's a one-way travel. Networks neural networks don't work like that. Your back propagation helps. So that's one fundamentally different. How do you build the control system application? It's interesting to see all this graph, but probably that's
okay. To answer that, whether I'm going by this or this, it's a feedback.
No, it's not a feedback. It's a back propagation.
It's a back propagation. But what is doing? You are trying to readjust those weights, isn't it?
Okay, so we'll discuss separately. I think on the second issue, once you're looking at the stability of the things, or the neural networks, you say stable or not. Otherwise, there is a very strong mathematical theory of checking for each layer of this. You can see the VC dimension of that and see whether the data sets get shattered by that VC dimension. You have an assurance of that, okay, this layer is my stable. That's how we used to stop the convergence of the particular layer. Okay. So generally what this kind of mature models which come up, they have generally gone through this process and they have ensured that the layer-wise stability is ensured and that then the overall system is kind of working. Most of the models which are these, they are available for the people to explore and work. But once you are looking for the actual models where the value is, their models are classified. You don't have access and they are not into the formats which you can decode. How do you access those problems? Because these are open model like the Google ImageNet or that model which is the 2014 paper actually covers everything. However, this neural net gives you a much better and simpler explanation and gets you access to the data. But when the models are closed, then how do you access it? That becomes a major problem because then you don't have access to these libraries to go and see in this.
Yeah. So here the prerequisite is to have a model, right? So, so his completely is AI model. I should have access to AI model. Once I have whatever format I have, it's done over there. So if you go to DeepSeek, Hugging Face, everything is available. I have all those 50 safe tensors available with me. I can do the reverse engineering on that. Yeah.
Yeah.
Minimum? Yeah.
Can you do that? Can you actually do that?
APIs, that is another. The requirement is of a model. I have access to the model. You have access. Are you getting the complete model with you? Can you get the complete entire model? Can you fetch that model? Yeah, certainly. When it is hosted over there, it is serving over there, it's available into your directory. So you can extract that. Same thing, if you go to the embedded systems where it is deployed as either HDF file or whatever, right? You can reverse engineer on that and do the reverse, as a firmware reverse engineering.
Quickly, last two questions, please.
Hi, Vivek. So it was a very inspiring presentation and thank you so much for sharing this information. So our team usually does adversarial attacks on predictive AI models using adversarial robustness toolkit. So as a part of my job, I go through a lot of white papers that are there in different attacks, that is like zero-order optimization and fast gradient attacks and everything. But can you share one learning resource that you think academically, even if it contains a lot of mathematics, is useful for adversarial researchers like us who to basically get into the momentum? Because we can go through a lot of white papers, but whatever is the basic need that defines the approach for this type of adversarial mentality, can you please suggest any learning resources based on this?
To be very honest, I started learning from Andrew Ng a couple of years back. So if you understand the mathematics that Andrew Ng explains.
So I'm an ML developer who turned into a cybersecurity researcher.
Yeah.
So I've gone through the entire ML development. I'm aware of it. How the models, biases and weights work, everything. But the problem is a developer is a developer. But what an attacker really does good is he pivots the model against itself. So that sort of mentality, if you have any resources, please share.
Honestly speaking, I don't have that resources. Whatever I learned from the courses and did my experimentations on developing the models, right? Where the mathematical things comes into the picture, that helps me to, give a thought in that direction. Thank you.
Yes, sorry, the time constraint. Only last question, and then I kindly request you all to connect to the speaker offline. Thank you.
Yeah, hello, sir. So, being a black box attacker, I mean, how we can start with? I understand the entire flow, and you said like we can do reverse engineering. But my point is, I am using one of the foundation model, and I am trying to build my application. But how do I get access of internal stuff where I can do an attack? So,
to the model itself?
To the model itself, or like you did this reverse engineering and all. So assumption is you have some hold of that data. But how that data, as sir told, like it will be closed. But you said for Hugging Face and some other places, it will be open. But it is not true in all the cases. So how will get the data where we can do the attack? As of now, we can do only prompt injection or some boundary attack or zeroth optimization or some pixel change of a violent attack is there, WNK, and some more image type of attacks are there. That we do without having the knowledge of how ML works.
Yeah.
But when we want to do the reverse engineering, we should get the data.
Yes, you should get model. That's it.
So model access should be there. So
yeah, you should have extract model. So if you have it deployed on the embedded systems, right, you have to extract the binary, right?
Okay.
There you will see separate files, maybe SDF file that you get, and you reverse engineering on that. Similarly, onnx is also deployed on the edge devices as well.
So suppose I get that one, and I can do all these changes, whatever you showed, maybe some small change I can do. Then we can pack and we can put it in our embedded device once again. That will be impact only me, but it will not impact other folks. Then how can it be considered as a attack?
Because if I'm going to reverse the model, right? See, first thing is I get the entire architecture, right? So I have the architecture with me that breaks the confidentiality. That is the first step, right? So C part is gone. Now considering the I part, the integrity part over here, right? If I can, reverse engineer in terms of, not randomly changing the weights, but understanding which weights are actually susceptible to that. I can pack those weights because all those weights you can get in a numpy file. Together you have combined over there, and onnx is a format which is very flexible, interoperable. You can convert any format into onnx. So initially when I start doing, before having this Netron tool, most of the things I did is convert any model you get into open neural network exchange. So that helped me to understand what is there inside architecture, whether it's PB or whatever. Yeah.
And those models we can hosted the Google website or somewhere also.
Yeah. Okay. So today,
Yeah. Thank you very much, sir.
Yes, guys. That indeed was a really thoughtful and informative session from you, Yashodhan.
Thank you. Thank you so much. Thank you.